Today we're going to talk about bond enthalpy. Specifically, we'll talk about how to use bond enthalpies to determine the enthalpy of reaction. Now, to review, the enthalpy of reaction, also abbreviated delta H with subscript Rxn or reaction, is the heat absorbed or released during a chemical reaction. During chemical reactions, bonds can break or reform or both, and when they do, they either absorb or release energy. Breaking bonds between atoms always requires adding energy. The stronger the bond, the more energy it takes to break it. Forming bonds releases energy. The stronger the bond formed, the more energy is released. There are four main ways we calculate the enthalpy of reaction in AP chemistry. The first is calorimetry, and we've seen this in previous topics. The second is using bond enthalpy, and that's what we'll talk about today. You can also calculate it using enthalpies of formation and Hess's law, and these will be coming up in future videos. So what is bond enthalpy? Well, bond enthalpy, also called bond dissociation enthalpy or average bond energy or bond strength, is the energy needed to break up 1 mole of a bond into its separate atoms. Bond enthalpy is specific to molecules that are in their gaseous state. And I want to emphasize the gaseous state part here because some of the other ways we calculate enthalpy of reaction can be done with reactants that are in other phases. But here we're dealing with gas. Bond enthalpies are always positive for breaking bonds. Since breaking bonds takes energy, it's endothermic. Remember, it takes to break. Bond enthalpies are negative if you're forming bonds, since forming bonds releases energy. It's exothermic. So let's talk about how to use these to determine the enthalpy of reaction. Bond enthalpies are determined experimentally, and there are tables that show the enthalpies for different types of bonds. Because the bond energies between two atoms vary a little bit depending on what's around them, and when I say this, I mean the other bonds in the molecule, these bond enthalpies you find in tables are average values. Now we can calculate the enthalpy of reaction by adding up the energies absorbed or released by the individual bonds that are breaking and forming in the reaction. Let's take a look at a table of bond enthalpies. Notice that the bond enthalpies differ depending on the atoms and on the order of the bond. In other words, whether it's single, double, or triple. The higher the bond order, the higher the bond energy, and this should make sense. So here's how to find the enthalpy changes of a reaction using bond enthalpies. The enthalpy of reaction equals the sum of the bond enthalpies for the bonds broken minus the sum of the bond enthalpies for the bonds formed. And you know how I mentioned earlier that the enthalpies of the bonds formed are negative? Well, the minus sign in this equation takes this into account. So we don't have to keep track of positive and negative. This equation keeps track of it for us. Here's a memory aid.
Basketball is my best friend.
Bonds broken minus bonds formed. If that helps you, use it. So let's talk about the steps we can use to determine the enthalpy of reaction from bond enthalpies. Step 1. We are going to determine the delta H for the bonds that are broken. First thing to do is to draw out the molecules so that we can visualize which bonds are breaking. Then we're going to look at a table and we'll find the bond enthalpies for each of the breaking bonds. We'll add these values all up, but we need to pay attention to stoichiometry because if there are multiple copies of a type of bond, you have to multiply that bond enthalpy by the number of copies of that bond in the reaction. In step 2, we're going to do the same thing for the enthalpies of the bonds that are forming. We're going to draw out our molecules, we're going to look at the table and find the bond enthalpies, and we're going to add up all of these values but account for the number of copies for the stoichiometry. Finally, we're going to use our equation to solve for the enthalpy of reaction. This equation is not on the formula sheet you'll be given for the AP exam, so you're going to have to memorize how to do this. Think about the memory aid.
Basketball is my best friend.
Bonds broken minus bonds formed. So let's do an example. Find the enthalpy of reaction for the following reaction using bond enthalpies. And here's the equation. 2H2 gas plus O2 gas yields 2H2O gas. And notice that all of these are in the gaseous state, which it has to be if you're using bond enthalpies. So for our first step, we're going to calculate the total bond enthalpies for the bonds broken. We're going to draw out the molecules and determine which bonds are breaking. If we Lewis structure out the molecules in our equation, we'll see that we have at least one hydrogen-hydrogen single bond and at least one oxygen-oxygen double bond. We are going to go to our table and we're going to look up the bond enthalpies for these types of bonds. Now, we see that the bond enthalpy for HH bonds is 436 kilojoules per mole. We also see that the bond enthalpy for oxygen-oxygen double bonds is 499 kilojoules per mole. Now, when we go back to our equation, we notice that we have two hydrogen molecules in our reactant. So we are going to have to multiply the bond enthalpy by 2, and this will give us 872 kilojoules per mole. Now, the last thing we have to do for this part is to add up the total energy of the bonds broken. And that's going to be 872 kilojoules per mole plus 499 kilojoules per mole, and that will equal 1,371 kilojoules per mole, the energy that is absorbed when bonds break. Our next step is going to be to determine the sum of the enthalpies for the bonds that are forming. As we did before, we're going to draw out our molecules and we're going to determine what bonds are being formed. And we see when we draw the Lewis structure of water that each molecule is going to have two single OH bonds. Next, we're going to find the bond enthalpies for the bonds being formed, and our OH bond has a bond enthalpy from the table of 463 kilojoules per mole. Because we have two water molecules, and because each of these molecules has two oxygen-hydrogen single bonds, we're going to have to multiply the bond enthalpy by 4. So we'll take our 463 kilojoules per mole and multiply it by 4 to get 1,852 kilojoules per mole. Now, we would typically add up the bond enthalpies of all the bonds in our products. However, we only have OH bonds, and we've already accounted for the stoichiometry, so this step is done. Next, we're going to use the equation to solve. So our heat of reaction is 1,371 kilojoules per mole minus 1,852 kilojoules per mole, and that gives us negative 481 kilojoules per mole. This reaction is exothermic because our enthalpy of reaction is negative. And this implies that the energy released when bonds are formed is greater than the energy absorbed when bonds are broken. Let's do another example. It's a little bit more complicated. The equation below shows the complete reaction of propane. Use bond enthalpies to find the enthalpy of reaction. Now, just like in our previous example, our first step will be to determine the sum of the bond enthalpies for the bonds broken. So first we're going to draw out our molecules and determine which bonds are breaking. So here we have a Lewis structure for propane, and we'll also draw out the Lewis structure for oxygen. We don't have to include the lone pairs because we're only interested in bonds. And we're going to figure out which bonds are breaking. And as we can see, we have 2 carbon-carbon bonds, 8 carbon-hydrogen bonds, and 5 oxygen-oxygen double bonds. And we have 5 of these because if we look at the stoichiometry, we have 5 O2 molecules. So now we're going to go to our table and we're going to find the bond enthalpies of each of these types of bonds. Now, when we take a look at our equation again, notice that we have a lot of coefficients here. There's a lot of stoichiometry going on. And when you have so much going on, sometimes it's useful to make a table. You don't have to, but let's go ahead and do that now. We have 8 CH bonds, so we're going to multiply 413 kilojoules per mole by 8, and that will give us 3,304 kilojoules per mole. We have 2 carbon-carbon bonds, so we're going to multiply our bond enthalpy by 2 to give us 694 kilojoules per mole. And we have 5 oxygen molecules, and that means 5 oxygen-oxygen double bonds. And we're going to multiply that by 5 to get 2,490 kilojoules per mole. And if we total all of these up, we get 6,488 kilojoules per mole. And this is the sum of the enthalpies for our bonds broken. Now we're going to do the same thing for our bonds formed. We have 3 carbon dioxide molecules, so let's draw a Lewis structure for a carbon dioxide here. And we have 4 water molecules, so we'll draw a Lewis structure for our water molecule. We've got 2 carbon-oxygen double bonds in every CO2 molecule, and we've got 3 of those. So we're going to have to take that into account when we add up our bond enthalpies. Likewise, we have 4 water molecules and each has 2 oxygen-hydrogen single bonds. So let's remember this for later. We'll look at our tables and we'll find the bond enthalpies for our carbon-oxygen bond, and we'll do the same thing for our hydrogen-oxygen bond. Now let's go back to our table so that we can take care of the stoichiometry. For our carbon-oxygen double bond, we have 3 molecules, each of which has 2 carbon-oxygen double bonds. So we are going to multiply our bond enthalpy by 6, and that'll give us 4,830 kilojoules per mole. For our hydrogen-oxygen single bond, we have 4 molecules, each of which has 2 copies of this. 4 times 2 equals 8, so we are going to multiply 8 times our bond enthalpy, and that will give us 3,712 kilojoules per mole. We're going to add all of these up and get a total of 8,542 kilojoules per mole. Now remember, we're using a table that reports the bond enthalpies for breaking these bonds. When we're forming bonds, the sign on this would be the opposite, and this is accounted for in the equation we'll be using. That minus sign there is doing the flipping for us. So we are going to substitute our values into this equation, and we see that the enthalpy of reaction is negative 2,054 kilojoules per mole. And because this value is negative, we know that the energy that was released when forming the bonds is greater than the energy that was absorbed when the bonds are broken, and hence our enthalpy of reaction is negative. So to summarize, you should now be able to calculate the enthalpy change of a reaction based on the average bond energies of bonds broken and formed in reaction.